What's the matter with you? In this chapter, we're going to build the basic vocabulary needed to describe all of our materials. And by all the materials, I mean matter. We will begin by examining the particular nature of matter and distinguishing between elements and compounds. We will then compare the solid, liquid, gas, and plasma states of matter. Next, we will then separate the physical properties and physical changes from chemical properties and chemical changes. That's 4 things. That'll be fun. And finally, we will organize matter into mixtures and pure substances, then look at 2 physical methods of separating mixtures. These classifications will appear throughout all of chemistry, so it's very important to understand not only the definitions, but also how the categories are connected. All right, section 2.1 will focus on the nature of matter. We have 3 objectives. First, we need to learn about the composition of matter, including the idea that matter is made of extremely small particles. Second, we will learn the difference between elements and compounds. Both are pure substances, but they differ in the number and kinds of atoms they contain. Third, we will define the 3 states of matter. There's 4. Solid, liquid, and gas. As we move through this section, pay attention to both the visible properties of each type of matter and the particle level pictures used to explain those properties. It'll come up a lot on the test and in some quizzes. The particulate matter of nature. If you know what the word particulate means, that'll help. Matter has mass and occupies space. In other words, matter has an amount that can be measured and it takes up room. Matter is also composed of tiny particles called atoms. The pennies shown on this slide, they don't make them now, or do they? Looks solid and continuous at our scale. But the enlarged particle picture represents the atoms that make up that material. We cannot actually see the individual atoms with our eyes, yet the arrangement and behavior determine the properties of the matter that we do observe. Throughout chemistry, we will frequently connect visible objects to their microscopic model of the atoms involved. Shout out 1981. You guys know I was not alive in 1981. An element contains only one kind of atom. Elemental copper contains only copper atoms. Elemental gold contains only gold atoms. The pictures at the bottom, look at them. Look at them, for real though. Show that this definition applies even when the atoms are arranged in different ways. Solid gold is represented by many individual gold atoms packed closely together. Hydrogen gas is showed as H2 molecules, with each molecule containing 2 hydrogen atoms bonded together. Hydrogen gas is still an element because every atom presented is a hydrogen atom. They're called diatomic. We'll talk about that later. The number of atoms joined together does not determine whether a substance is an element. What matters is whether it's only one kind of atom. Compounds. Compounds are substances that contain 2 or more kinds of atoms. This nifty table, 2.1, shows several familiar compounds and their atomic combinations. Carbon monoxide, contains 1 carbon and 1 oxygen. Carbon dioxide contains 1 carbon and 2 oxygens. Water contains hydrogen and oxygen, while hydrogen peroxide also contains hydrogen and oxygen, but not in the same ratio. These examples show some elements can form different compounds when their atoms are combined in different ratios. Each compound has its own characteristics. Carbon monoxide is poisonous. Carbon dioxide is produced as a waste material from breathing and other parts of metabolism. Water, the most essential liquid we've got, and hydrogen peroxide is used as a disinfectant or bleaching agent. Changing a single number when we make our molecular compounds changes the identity of that thing completely. Don't forget about that. Bum, bum, bum. The first concept check. We will have a lot of these. Some chapters have more than others. Get ready for these. You'll love them. How many of the following are considered elements? as opposed to compounds. Think back to the definition of an element. I'll give you a second. Have you thought about it? I hope so. Let's go through these. We have He. I don't know what that is, but it's probably one thing. I have F2. Looks like it's only got one thing. HCl. Who knows? I'd probably have to look at a periodic table. We should talk about that too. S8. Well, from what I know, He, since that E is on its own, right there, little e, lowercase e, that must be helium. And I don't see a number or anything with it, but even if I did, I think that would still count. It does. Helium is an element because it only contains helium atoms. There's one. F2 is an element because it contains only fluorine atoms. We would probably call that fluorine gas, but we don't know exactly because it didn't give us everything. S8 is sulfur octafluoride? Nope. Scratch that. It's just sulfur. 8 sulfur. I guess we'll have to talk about that later. HCl is one of the ones that's different than the rest. That would be hydrochloric acid, which we will talk about later, but it is a combination of two different atoms, a hydrogen and a chlorine. Remember, elements are substances that consist of a single atom or a group of that same atom. So it doesn't matter if we have 25 of them, or one of them, or two of them, as long as they are one kind of atom. Alrighty, states of matter, and you'll learn some random bits from this. We will talk about other states of matter that exist. A lot of times we say there are 4 states of matter, but there's actually a lot more than that. We'll get into more as extensions later on throughout this second semester, not as much in first, but let's talk about the main 3. All right, this might surprise some of you. We got solid, liquid, gas. Now, we know a solid is a tangible thing that is a shape. That's an easy one. Liquid, still pretty easy. It has a shape, but you only know that shape if it's in a container. And then gas, no shape unless it's in a container. So, uh, kind of similar, the definitions of liquid and gas, except that a liquid has a set amount of volume. A gas will fill an entire container. It doesn't matter how big it is. You'll know how I know is that we have an atmosphere. We'll talk about that one later. Notice that all 3 of these forms are made up of H2O molecules or water. We call those state changes because none of them change from being water. Their chemical identity is the same throughout each phase change. Alrighty, section 2.2 focuses on the properties of matter. We've got 2 objectives. First, we need to learn how to distinguish between a physical and a chemical property. A property is a description of a characteristic of a substance. But we need to determine whether observing that property changes the substance into something new. We'll get there. I know that sounded confusing. And second, we will learn to distinguish between a physical and a chemical change. The central question will be whether the composition, or what it's made up of, remains the same, or whether one or more of the new substances are produced. Keep that question in mind, and it'll make it easier to classify these examples. Matter has both physical and chemical properties. Chemical properties describe a substance's ability to change into a different substance. They tell us what kinds of chemical changes a substance is capable of undergoing. Physical properties are characteristics that can be observed without changing the substance into another substance. The slide lists shape, size, and color as examples of physical properties. We can observe or measure those characteristics while the substance keeps that same composition. The key distinction is not simply whether something can be seen. The important question is whether determining the property requires the material to become a different substance. Yes, we'll get into that. Matter undergoes physical and chemical changes. A physical change involves a change to one or more of the physical properties. but there is no change in composition. The diagram, right there, uses water as our example. Solid ice can melt and become liquid water, and liquid water can boil to become gaseous steam. The shape, arrangement, spacing, motion of the particles change, but the particles are still water molecules, H2O. No new substances produced, melting or boiling. Changes of state are therefore physical changes. When classifying a change, focus on whether the chemical identity of the material remains the same before and after the change. A chemical change is a change that transforms a substance into one or more new substances. This slide contrasts with physical change, which changes physical properties without changing composition. In this particle diagram, water molecules are exposed to an electric current. The water molecules are rearranged to form hydrogen molecules and oxygen molecules. Because the substances present after the change are different from the starting substance, this is a chemical change. Atoms are not created or destroyed in this process. We'll talk about why that's important. Instead, the atoms are reorganized into new combinations. The production of new substances is the defining feature of a chemical change. I hope you're ready, because you already know it's time for concept check. All right, we need to determine which of these examples are going to be a chemical change. I'll give you a second. All right, did you guys get it? Let's go through these. Pulverizing, if you don't know that, means crushing. Rock salt, burning of wood, boiling of water, melting a popsicle on a warm summer day. Rest in peace, summer. We'll see you again. All right, so let's go through these one at a time. Pulverizing rock salt changes its shape, but it's still rock salt. If I have a big chunk of salt and I break it, I now have smaller pieces of salt. So that is not a chemical change. Burning of wood. Burning seems to be a chemical reaction that produces things like soot, carbon monoxide, carbon dioxide, and water. I think all those things I named are not wood, which must mean burning wood is a chemical change. Woo, yeah, we did it. But we should probably check the other two. Boiling water. Is steam, after I've boiled liquid water, still water? If yes, not chemical change. It's yes. Melting a popsicle on a warm summer day is not a whole lot different than boiling water. We've changed from a solid to a liquid state. It's melted popsicle still. So it looks like we nailed it. Whoosh. The best question to ask yourself if you're saying, is this a chemical change, is did the composition change? Do I have something different than I started with? Yes. Section 2.3. We will focus on classifying matter here. We have two objectives. The first, we will learn to distinguish between a mixture and a pure substance. This classification depends on whether the composition can vary or must remain constant. We will also divide mixtures into homogeneous and heterogeneous mixtures, and pure substance into elements and compounds. Second, we will learn two methods used to separate mixtures, distillation and filtration. These methods are physical processes because they separate substances that are already present rather than changing them into new substances. All right, you're going to want to check out my chain. It's not 24 karat gold. Matter can be classified as either a mixture or a substance, a pure substance. The gold examples right here help show you the difference. 24 karat gold is represented as 100% gold. It's a pure substance. It's just gold atoms. 18 karat gold contains gold mixed with silver and copper. 14 karat gold is also a mixture of gold, silver, and copper, but in a different proportion. The lower karat mixtures are mixtures because their composition includes more than one substance, and the proportions can vary. The particle diagrams and bar graphs emphasize that the sample can look uniform, Gold looks like gold, even if it's 14 karat, while still containing several substances. Classification depends on composition, not simply whether the different components are visible. That's an important one to remember. Mixtures. What? A mixture has variable composition. That just means that the substance in the mixture can be present in different proportions while the material is still considered the same general type of mixture. A homogeneous mixture, homo meaning the same, has the same properties throughout. Doesn't matter how you cut it, slice it, stab it, slurp it, whatever. They're distributed evenly throughout the entire thing. Heterogeneous mixtures have different properties in different parts of the mixture. Its composition is not uniform then from place to place. In both cases, the substances are physically combined rather than chemically joined into a pure substance. Because the components keep to their own identities, mixtures can be separated using physical properties. And methods. Pure substance. A pure substance always has the same composition. A pure substance is divided into two types. We have elements, which we learned about, and compounds, which we technically learned about, but not really. An element cannot be broken down chemically into a simpler substance. It contains one kind of atom. A compound can be chemically broken down into separate elements because it contains two or more kinds of atoms that are joined in a fixed combination. The particle picture that you see down here shows water as an example of a compound. Every particle shown is the same H2O molecule, which means it has a constant composition. Although water contains both hydrogen and oxygen atoms, it's still a pure substance because every portion of pure water contains the same type of molecule and the exact same composition. Concept check. Which of the following is a homogeneous mixture? Think about it. Which one is it? Just keep thinking about it though. Like, I don't know. Is it a jar of jelly beans? Is it pure water? Soil? Gasoline? Copper, metal? I guess we should probably tell you. Pure water sounds like it's a compound, which would make it not a mixture. So I'm gonna throw that one out. Copper metal. That's copper. That's probably an element. Soil. I don't know if you guys have recently seen soil. Go to your mind palace now and envision soil. It's probably got like rocks in that dirt and stuff, which must mean it's a heterogeneous mixture. Because if I reached into one plot of soil, I'm going to have different stuff in my hand than if I reached into another. So probably not that one. A jar of jelly beans. Now here's the fun one that sometimes comes up. A jar of jelly beans is, we're going to assume, just a standard bag and not just the reds that you all want that are the Starburst flavors. We're going to assume they're different shapes and sizes, different flavors. So it's not the jar of jelly beans. That would be a heterogeneous mixture, which means we're only left with the thing that looks uniform, gasoline. It contains multiple substances, but it is properly mixed as a sample, and it has the same overall properties throughout. Doesn't matter where you sample your gasoline from, it's all going to have the same properties. So homogeneous means uniform throughout, but it does not only mean one substance present. So don't forget that when you take your test. Separation of mixtures. Mixtures can be separated into pure substances by several physical methods. This slide is going to show you distillation using salt water. The salt water mixture over there on the left side is heated in the first flask. The water changes to steam and leaves the flask while the salt remains behind. The steam moves through the condenser and is a tube that's cooled by flowing water. And as the steam is losing its energy from that flowing water in the condenser, it changes back into a liquid and it collects in the receiving flask. After the water is boiled away, the salt remains in the original flask and the purified water is now in the collection flask. Distillation separates the components without converting the salt or the water into new substances. The salt just went through, uh, it was dissolved, and then it was no longer dissolved because we put the water through physical changes. The last form of separation of mixtures is filtration. Filtration in this diagram shows that a mixture is containing both a solid and a liquid, and it's poured into a funnel lined with filter paper. The filter paper traps those solid particles, whatever they may be, because they're too large to pass through their openings. Then the liquid passes through the filter and collects in the beaker below. The liquid that passed through the filter is called the filtrate, another vocab word. Filtration works when an insoluble solid is mixed with a liquid. It doesn't chemically change the liquid or the solid, it just separates them based on a physical difference in their particle size and whether material can pass through the filter. There are different specific types of this kind of separation. We can have magnetic filtration, where we just have a magnet before we filter it and it takes out anything that's ferrous. There's lots of different ways of separating mixtures. We'll talk about those more as we move on in class. Finally, this diagram right here will summarize how matter is organized. And we're not really going to change this throughout the entire semester. So let's look at how it's organized. Matter can be classified as a mixture or a pure substance. We know that. Mixtures can be homogeneous, meaning they're uniform throughout, or heterogeneous, which means they are different in different regions of the mixture. Both types of mixtures can be separated into pure substances using physical methods, such as distillation and filtration. Pure substances are divided into elements and compounds. Elements cannot be broken down chemically into simpler substances. Compounds contain more than one kind of atom in a fixed composition and can be broken down into elements by chemical methods. The most important distinction is that a physical method separates substances already present in a mixture, while chemical methods separate a compound into different substances. You've done it. Chapter 2 is complete.